So thanks for the introduction. We heard today already a couple of times that all the machinery, all these nice products and technologies are driven by something that we know as deep learning. And this is a very exciting area. If you think about AI, one of the hottest areas is deep learning, fueling actually the entire AI movement. So we'll speak today about deep learning in the future of AI, how I see it or how the community sees it. So first of all, I always like to start with some slides, politically motivated. You know this lady, Chancellor Merkel. She said, "Das Internet ist für uns alle Neuland." It's a white spot on the map. That was 2013, not in the 90s, right, where the internet was invented, but 2013, in particular context with respect to Snowden. 2013. And then the next slide, you see the former President Barack Obama, where he said, "My successor will govern a country being transformed by AI." Two things, right? First of all, he did not know that Trump will be his successor, so he was very optimistic at that point in time. And secondly, what the heck happened between the internet is new and the society will be transformed by AI in 3 years? So that's also a little bit giving a pointer to the difference between Silicon Valley, US, and Germany. So what happened was actually this. So we see here, we saw this slide already in the first presentation. This is a very important turning point where a machine, artificial intelligence, won in a very complex game called Go against a human, not only a human, but the best, the world champion in Go, Lee Sedol, in 5 games. That was in March 2016, and as already mentioned this morning, many people believe that it will take decades to really conquer that game by a machine, and suddenly it happened by DeepMind. And the game, or the AI AlphaGo. So what was interesting here, I talked to the DeepMind people. Lee Sedol, when he came, he was very confident in not losing, right? So he thought he would go to this game, play around, and will not lose. And suddenly he was losing that entire game. There were 5 games. The first 3 were won by the machine. The 4th game was won by the human. And the 5th game, again, was won by the machine. So I think the 4th game, the Google engineers tuned a little bit the parameters so that the human will win. However, there are some memes, or today people would call fake news on the internet. So everyone thinks Lee Sedol won, but did you have a look at the black piece pattern at the whiteboard? So at that point in time, I mean, that beautifully kind of summarizes the zeitgeist that we have around artificial intelligence, right? Half of the audience is like sci-fi enthusiastic, embracing this great time, and the other half is like, oh, well, let's see how it develops. And this is suddenly moving into this direction where people currently are very excited, and this is very news. Thanks, Judith, for the pointer to this. Very recent news, Mark Cobain, who said, the first trillionaire will be an artificial intelligence entrepreneur. If you're not getting up to speed on deep learning, neural networks, you lose. Very strong statement, right? So this is something that, again, puts an emphasis on deep learning and how important and what kind of impact that has. So I would like to go to a particular year, it's 2012, where we really saw a revolution. So there are 2 types of research, right? There's this slow step-by-step type of research reaching a boundary, and then there's this kind of revolutionary impact that kind of explodes this boundary and redefines the rules of research. And we are lucky that we were in 2012 at this very moment where the rules were kind of newly defined and a revolution started in deep learning. So what was that behind? It's all about neural networks. So neural networks is a particular part inside of the AI research area that deals with the simulation of the human brain on machines, right? It's a very old topic, as old as we have computers. People actually try to simulate the human brain that consists of neurons being connected on a machine mathematically to simulate this activity inside of a human brain on a machine. And it's very old, and in 2012 it really changed the status quo of artificial intelligence. So when we summarize what we actually want to do, you see it here. We have particular tasks. For example, you have a picture, and then you have a human. Human looks at the picture and says, that's a flower. We have another task, a driving situation, human can say, drive carefully due to the current traffic situation. Or as we saw, the game, least at all, played, and then the human who kind of moves the pieces in a way that he maximizes his gain and wins finally the match. So what we have here are humans in the middle of that act as an end-to-end learning system, right? We cannot look in the brains of the humans in that detail, but somehow we can map the input, a picture with pixels, to an output that's a flower. And that's actually a very powerful mapping mechanism, and this is what neural networks try to do, also in an end-to-end learning scenario in a linear mapping. So that's the idea. You don't really know what's happening inside, but you very much appreciate this mapping between an input and an output, and you need this input and output pairs to train the neural networks, and this is why we need this huge amount of training data to really be able to create this mapping. And this is parameter feeding, this is called training, and here we see what happens. So when we look a little bit into detail, we will see that this idea of training a neural network is actually not a new one, right? So we had this already as long as we have computers, and there are some very important items like Lunette in 1989, where particular tasks were solved by neural networks. Here, handwriting recognition was great, it worked in that area, it didn't work in other areas, right? So when I speak to people, there's always one guy who says like, neural networks, we had it in the 90s, it didn't work, right? So then suddenly, AlexNet came. So we see here, first of all, computer science guys cannot draw pictures, nice pictures. Very complicated. That's the AlexNet architecture. This is the reason we have the success today. This is a deep neural network, a particular type of deep neural network called convolution neural network. And you see here in 2012 that this AlexNet, created by Alex Kraszewski, was put into an ImageNet challenge and won against all the other competitors, against all the other machine learning, artificial intelligence methods. It did not only win, it won with a huge gap. And everybody was surprised, like, what the heck is happening here, right? Those things are not working. Why are they suddenly working? And there's a good reason why they're working, because three things came together. First of all, we have a learning mechanism that has a variable capacity of learning. We can increase the capacity of learning by increasing the neurons and increasing the layers in the network. The more layers, the more capacity do we have for learning. Problem? We have to train that. More layers means more free parameters. We need the data. And in 2012, we had the data with the ImageNet challenge. As you see here, suddenly there were much more data items to fit those parameters inside of the training method. So the only thing that was missing was actually the machinery that is able to crunch the numbers to do the training. And here, one of the very ironic, sarcastic things happened. People misused GPUs, graphic cards, to train neural networks, right? So there were people who were misusing that, and a very interesting thing is that the CEO of Nvidia, who invented GPUs, did not suit those guys who misused their products or his products. He said, oh, well, that's interesting. Let's see what we can do. Let's support those people and give them more GPUs to do better work, right? So, and then suddenly, all the things changed. 2012, AlexNet was created, and today, Nvidia is making 1.5 billion out of 5 billion revenue by graphic cards that will never ever see a monitor in their life. They don't even have a plug, right, to put a monitor in. They are entirely dedicated to train neural networks, shipped all to Google and Facebooks in large scale. So this is what happened. The three things came together, and that's the reason why 2012 is so important for deep learning with respect to that. So when we see those numbers, just to have an idea of the impact, so we see here the results of ImageNet. That's the error rate. So the smaller, the better. We see here the first traditional methods. Old school, right? Traditional for nice. 28 error, 25% error. And then suddenly AlexNet came, and you see this drop. So the first network had an architecture of 8 layers. And I asked a gentleman who gave the presentation this morning, who is a neural specialist. He said that the visual cortex has 7 layers. So when you compare the 7 layers of the visual cortex to the original architecture of AlexNet with the 8 layers, you know that the last layer is just the softmax. So actually the first people who invented the neural networks, they were trying to simulate the visual cortex for this task of ImageNet, recognizing objects like flowers in images. So that was the first architecture, but an interesting thing happened. Everything suddenly was open sourced, a system where you can train neural networks was open source, Café, and the reference model was open source. So many people could just download that and improve the architectures, make those networks deeper, which means adding more layers, like VGGNet, and then we had GoogleNet, the Inception architecture, up to a very important moment in time, 2015, where ResNet, with residential layers from Microsoft, came into being, and now we have neural networks that have hundreds, if not thousands of layers, right? Much further than what we have in the human brain, and they are much more capable. So the interesting part is we still see improvements in making those networks deeper. They have better performance, improve error detection, and this is interesting because we can now really see improvements in the perception process of that. So here, a very important, 5 years of research, right? We started with 8 layers, already millions of connections, up to billions of connections with hundreds of layers that we have currently, and there's no saturation seen, right? So we can there's still space to improve with respect to that. So when we then have this success of neural networks and everybody's happy, right? Suddenly we can build a self-driving car. We have this problem that we have to explain when the self-driving car has an accident, what happens inside of the network. So it's a very important task to kind of open this black box of neural networks to understand what's happening inside. And here are some slides showing you what's happening. So here you see 3 networks or 4 networks where you feed the image from the bottom to the top, and the first layers actually, they're gradient detectors, edge detectors, like, surprisingly, in our human brain, and you see really that they are all the same for different things, and when you go further and you kind of zoom into the network, you see there is a specialization up to the concepts that are detected like faces, cars, elephants, and chairs. So that's the power of deep learning. The first layers are very generic. They share their representation, its internal representation, share the weights, and then the specialization is happening in the middle and at the end of the layers, and therefore what people are currently using, they're taking a very powerful neural networks, throw away the concept, the cats and dogs, and train their own concepts, because suddenly with transfer learning, you can use this kind of power of generalizability of those networks to train new concepts and then suddenly scale up in recognizing your environment. So when you go further in trying to understand what is happening inside of neural networks, a beautiful work was presented by Google. Deep Dream was it called, 2015. So you see a picture, and then people tried to emphasize a neural network on top of the picture. People tried to kind of push hard so the network was forced to detect something, and indeed the network was detecting something. An admiral dog, a pig snail, a camel bird, and a dogfish, right? Inside of those cloud structures, like when we look up into the sky and see sometimes faces in the clouds. So what we see here is people are kind of they're talking about dreaming, right? So some kind of human behavior that is happening now on the machine. But what I actually see here is that is very nice, a very nice marketing gag from Google, but it's a huge problem for privacy, right? The models, the neural networks, they have a compressed representation of the data they were trained on. So when you want to train a face detector, it might be possible to reconstruct Mr. Müller's face. Privacy concerns, right? Not that many people are aware of that, that we have that. And there's also one point that is very important. I always talk to companies, right? The software is not as important anymore as previously. All those platforms are open source, TensorFlow, Café, Torch, and others. The important things are actually the models. And the models are important because they compress the data, and not everybody has the data. So as a company, be aware that your data is your IP, and don't give your data away, right? So when I speak to German car manufacturers, the self-driving OS, that's the thing that you develop and that you're not asking for Google to develop, because in the very moment you're giving it to Google, the data will be Google's. So one interesting thing is also that we're moving from an app store paradigm in having apps and software to a model store paradigm where we share models. So this is very important. If you think about the future, we will have trained models that we will trade. And that's the power, actually, that we have with the standardization of deep neural network frameworks like TensorFlow, for example, and others. So when we go further, also a very nice example from University of Tübingen and colleagues over there. So the task of deep neural networks until now was to have, for example, a picture, an unstructured document, and then to recognize concepts, right? as an analytical task. So what those guys did was very interesting because they reversed actually the function and they were creating content. So their idea was, you have a picture, Tübingen, and you have a style of an artist, and you can train a neural network on top of the style of a neural artist, and then you can fuse those two things together and create neural art. So you see this picture is being fused with this style and creates this beautiful image. And I mean, I would put it on the wall, it looks beautifully, and it also tells us something that until now we're always thinking that, you know, in the future we will have machines doing all the boring work, all the hard labor, and we will finally be free to be artists, poets, and writers, right? And suddenly those machines are being creative. And we can argue if this is creativity or copy-paste, right? But they are moving in areas that we were not expecting that they're able to move into. Another example of that, beautiful art that is created automatically. And people are actually using this, artists are really using this to create new art. And so the job of an artist is moving a little bit to a job of a programmer, which is also very interesting to see. So this is also a kind of interesting way of generating content by neural networks instead of just analyzing that content. So what we see as a next is one of our work that we actually work. We were the first team worldwide able to extract sentiment from visual content. So if something is positive or negative or has a positive or negative sentiment. What we see here is a video, and this is in collaboration of my former universities where I worked, UC Berkeley and Columbia University. What we see here is a video in real time that is running, and you see the top 3 so-called adjective-noun pairs, concepts that we see inside of the video with their sentiment, if something is positive or negative. So we can use, for example, surveillance, images, to really do targeted advertising with the right context, and here to build a map of Berlin, for example, given all the adjectives, which areas are beautiful, which areas are dangerous, which areas are dark, which areas are nice. We can take this objective measurement to a subjective perception, and now on top we can learn things like safety impressions or perception, real estate pricing. Actually, a big real estate company with 60 billion assets under management is very interested in that because they have to manage their actually assets in areas like India and China, and they don't want to send people all the time there when they're looking for new objects, right? So we can, on a large scale, automatically analyze that and provide this back. So very interesting work that was done now with deep learning, and the best part, because it's running on a GPU, it's able to do this in real time. So what we see here, that was also one of the reasons where Nvidia, in September last year, has awarded us with an Nvidia AI lab. There are only 2 Nvidia AI labs in Europe. It's us and our work and a lab in Switzerland. So we see here Jensen Huang, the CEO of Nvidia, and he shows me this is the deep learning supercomputer, what you see here, a so-called DGX-1. So he shows that, and you see he's smiling like a child on Christmas, like, look what I have, right? It's great. And the interesting part is, so we had a photo shooting with like 20 people from his staff. He also has a bodyguard. It's a kind of a cross section between a Navy SEAL and a hipster. So he can kill you and still look fashionable, right? And there was a fingerprint on this golden thing, right? So there were like 20 people, and he asked for a glove and was cleaning it, right? So he said, like, Damian, look, I'm a CEO of a multi-billion-dollar company, and I still have to do the work by myself, right? That's something that, you know, a founder that is still a CEO on a multi-billion-dollar company. There are not that many in Germany, right? There's a very strong character with a very great vision. So just to see what it means with respect to that. So the very first AlexNet that was trained in 2012, the guys needed 2 months of constant training of this machine, 2 months. In 2 years later, for 2 weeks with new improvements of hardware, last year in 2016, a new generation of GPUs came out, Pascal, 2 hours, just to get an idea of how much the hardware improves and how quicker we can train new neural networks with the idea that now you can go deeper, right? You can take more data to crunch. And this is also something that we see that there is still an improvement in the hardware which allows us to use more data for training to fit the parameters. The problem with deep neural networks is, and that's the reason it took so long until they were successful, it's a non-convex optimization problem, which means try and error. You cannot press a button and it's guaranteed to have the best neural network. You try and error, you try and error, you try and error, and then suddenly it works. So you have to reduce the time between starting your training and having a result to get rid of all the things that are not working and kind of follow the path along the things that are working. So I was actually yesterday or 2 days ago, I was in San Jose. They have the annual GPU technology conference, the so-called GDC. So by the talk, we're also part of the keynote. So the nice part is here, yesterday or 11th of May, Jensen also announced a new generation of GPUs, Volta. Within 1 year, from 2016 to 17, he increased even the kind of development of GPUs because in his basement, he has a bunch of GPUs, 1,000, the cluster is called Saturn 5, and they're doing nothing else than just improving the architecture of those chips. Machines building machines. And that's the reason he was able to do a new GPU architecture within 1 year. And you can see the stock price. I mean, the announcement was worth 10 billion of market capitalization. 1 day change, right? So that's what happens 2 days ago. And this is also a slide of the expanding universe of modern AI. So you see research labs, you see a technology provider, cloud computing platforms, startups, and you see established players, right? Not that many German companies, although we have Audi, there's Siemens somewhere. So there are some companies that are understanding that AI is important, right? So if you think about the DAX 30, not everybody is understanding that on the C-level. Some people are understanding, some people take longer to understand, and then they have trouble in recruiting, but it's not so evident like it is in the US. And what we see here in this market is not only AI as a new industry, it's a disrupting force in every single industry. Started in automotive, moving quickly to retail, finance. This year, finance is really crazy about changing due to regulation of next year. Medical, pharmaceutical is moving from one industry to another, and there's an estimated market of $500 billion US, and there are already $5 billion US in VC money invested in companies. And we have to be very careful in academia to have an expectation management here, because we are not supposed to promise too much, because we know that there were AI winters, and we have to be very careful in kind of taking care of AI to not kind of overpromise and underdeliver. So that's very important in this situation. However, we also have a responsibility for society. So besides and beyond all these great commercial products that we can build and all these achievements in AI, suddenly we can do things that were a couple of years before actually science fiction. There's a responsibility in the society. So we have to think very strongly about, to speak to people in society about where to draw the line, right? Where do we have to actually stop with the AI and the application of AI? And this is something that not a Mark Zuckerberg or a Sergey Brin should decide, or a politician, but society. So we have to go and speak to the people to find a consensus about what should we do and what not. And it's very important to also take the magic away of this machine, right? There is no magic inside. It's a complex machinery that is working perfectly, but it's no magic. So we are actually with the Volkswagen Stiftung in a very strong program that will start next year about AI and society, about changing that. And also there's a lot of work about regulations. And this is really important. This market is not regulated now. You can do whatever you want. And there will be a demand for regulation. So it's very important to first classify there are AI systems that have a direct impact of human life. Self-driving cars, robots, surgeons, etc. And there are AI systems that classify cats and dogs, right? It's not that important. We should focus on those AIs that need more money and time to think about what they can do, and also not focus too much on the others. So at the end, we have to start with a classification system for AI systems, and then we have to build an AI TÜV compliance. So that's a great area where we can build beautiful startups that you can actually think about, go to a company, like a large-scale company, Daimler, and ask them, what kind of AI systems do you have in-house? They have no idea. What kind of data do you have? Is it trained? Which versions? What the error rates, right? No idea, right? And there will be the demand to answer that questions, and this is a great place actually for startups. And then if you think about 5 to 10 years, I promise there will be the headline, I'm just making up the companies, BMW AI, hacked Daimler AI, right? And then people say, oh, well, it's not our fault, AI, right? Right? There will be a need for AI law enforcement. And that comes hand in hand with the regulation, right? So we will have this kind of implications that responsibility of an AI, self-acting, will be not in the hand of the company, or will it be in the hand of a company? How to deal with that, right? So beautiful questions that we have. And last but not least, we also have a machine learning online course, the very first German machine learning online course that we have created at the CeBIT, already 5,000 people. It's all free, 38 clips, not only academia, but we have beautifully people from Google, from Nvidia, Amazon. So that was very important when I spoke to Mr. Kagemann and Mr. Walster, when I designed the curriculum, to have not only the kind of boring stuff, but also the interesting stuff, right, to motivate. So go for it. It's all open source. It's all free to watch. The forums are closed, but it's still there. And then with the last slide today, I would like to say, those are two of my heroes in Silicon Valley, Chuck Geschke and John Warnock, the founders of Adobe, a truly startup. They said when they actually developed the desktop publishing industry with Photoshop, Illustrator, and PostScript. So they said we were in the middle of a revolution and we were aware about our responsibility. So we are today in the middle of a revolution with AI. And I'm wondering who is aware of the responsibility that is actually actively modifying and pushing this area. So it's also very important to not only think about all these beautiful developments, but also about responsibility. And maybe you can connect both and get a great startup idea for that. Thanks a lot for your time.